Compound Inequalities Introduction. Consider the sentences Mr. Pham teaches math and history versus Mr. Pham teaches math or history. In saying that Mr. Pham teaches both math and history, this sentence is false because the only class that I teach is math. I don't teach math and history, I just teach math. In contrast, the sentence Mr. Pham teaches math or history, well, this one is true because it's saying Mr. Pham teaches math or Mr. Pham teaches history class. And since I do teach math, it is true. So what seems to be the difference here? Well, the difference is the word and versus the word or. And that's going to be key to our lesson here. The sentences above are compound sentences because they combine multiple ideas. And so in math, we have what are called compound inequalities, which are two or more inequalities joined by the word and or the word or. So the word and is true when each inequality is true. And we have some examples off to the right. 1 less than or equal to x, and x is less than 7. And as it turns out, when we have the and compound inequalities, we can actually condense them into one single super inequality, right? 1 is less than x, and x is less than 7. The other compound inequality is the or statement, and or is true when at least one of the inequalities is true. So we, as the example, x is greater than 2 or x is less than or equal to -1. So in exercise 1, we want to determine whether the entire statement is true or false. So here we have 7 is greater than 3 and 2 is less than 10. Well, the compound the conjoiner is the and 7 greater than 3 is true. 2 less than 10 is true. Okay, and looking at the table above, the overall statement is true if every inequality is true. Well, there's 2 inequalities here, and they're both true. So overall, the entire thing is true. So it's true since every part is true, which it needs to be. So it's true since every part is true for and. Okay, in part B, we have 5 is less than 10. Well, that is certainly true. Our word is and we have 11 is greater than 20. Well, 11 is not bigger than 20, so that's false. And so we have a true statement and we have a false statement. Well, the requirement for and is that both must be true. Since one of them is false, the overall statement is false. So it's false since not every inequality is true. Now in part C, we have -4 is less than 7. Well, that's true. Here we have the word or, and 8 less than 2. Well, 8 is not less than 2. That's false. So we have true or false. Well, looking at the definition above, for an or compound, it is going to be true as long as one of the inequalities is true. And notice that one of the inequalities is true. So overall, this is true for or, since at least one is true. Okay. Part D, 3 is greater than 6. Well, that's false. And then 8 less than 5. That's also false. So we have false or false. Now remember, by definition, or requires at least one of them to be true. Well, since all of them are false, this is overall false. Okay, so the big takeaway here is when we are combining inequalities using the word and, every inequality must be true. When we're dealing with or, at least one of the inequalities must be true. Now, inequalities involving the word and are almost universally written as a single inequality because these tend to show us how all values of x are between two numbers. Namely, the format that we're going to do is we have the lower number is going to be smaller than x versus some high number. So x must be bigger than the low number, and it must be smaller than the high number. And then we're able to then break this up into the low number is smaller than x, and then x is smaller than the high number. So I'll show you what I mean. Rewrite each inequality as two inequalities using the AND connector. Oops, we're not going to worry about graphing yet. So here, this is saying -4 is less than or equal to x. So we can say -4 is less than or equal to x, and at the same time, x must be smaller than 6. Okay, go ahead and try to do part B. So for part B, hopefully we wrote -5 is less than or equal to x, and x is less than or equal to 9. Now in exercise 3, we're going to do the opposite. We are going to rewrite these two inequalities as a single combined inequality. Now notice for exercise 3, the format's a little bit off. Like here we have x is greater than or equal to -5. Because we are used to saying the lower number is less than x, we can actually flip this around. Right? I'm flipping the entire inequality. So not just the inequality symbol, but the 5 is now on the other side, the inequality symbol has been flipped, and then the x is on the other side as well. And so now, this is in a format that makes a little bit more sense. Right? -5 is less than or equal to x, but at the same time, x is less than or equal to 10. Okay, pause the video and try to do part B on your own now. So for part B, here we have x is less than 12, right? I'm kind of flipping it. And at the same time, 7 is less than x. So here we have our x. We know that x must be bigger than 7. And at the same time, x is less than 12. Okay, moving on. So now that we know how the definition of inequalities, next what we're interested in doing is graphing. So for the word and, that's going to be where the graphs of the individual inequalities overlap. This is also called the intersection of the graphs. So what I mean is that 1 less than or equal to x less than 7. Well, this is really 1 less than or equal to x, and x is less than 7. So what we can do is we can graph each inequality individually. So up above, we have the graph of just 1 is less than or equal to x. This means we have a closed circle at 1, and our values of x are everything to the right. Okay, that's just the graph of 1 less than or equal to x. Underneath that, we'll do the graph of x is less than 7. Now in this case, we have an open circle at 7, and then we graph everything to the left, because it's everything smaller. So right now, the only thing I have is the graph of 1 less than or equal to x, and the graph of x is less than 7. The graph for the compound inequality is going to be where these two graphs overlap each other if you were to put them on top of each other. So what will end up happening is, notice that this section over here, if you put the graphs on top of each other, they won't overlap. Over here to the right, if you put the graphs on top of each other, they won't overlap. The only parts that will overlap is this middle section right here. Now what we have to be careful of though is at the value of 1, notice that the first graph is filled in and the second graph is filled in. So in the overlap, we will be filled in there. What's tricky is look at x equals to 7. In the first graph, it is filled in here. And in the second graph, it's not filled. Now remember, the definition of intersection is that it needs to be fit true for both graphs. Because it's not true at 7 for both graphs, the result is not filled in. Okay. Now, for the OR graph, the OR graph is the union of the graphs, and what that means is as long as it's filled in somewhere, it will be filled in the final graph. So what I mean by that is consider x is greater than 2. So we have an open circle at 2, and everything to bigger. For the inequality, x is less than or equal to -1. We'll fill it in at -1. Everything smaller than that. So for the compound graph then, what you can think about is if you put the graphs on top of each other, any part that is shaded for the individual inequalities will be part of the answer. Right? Notice that the graph really is what you would get if you put the graphs on top of each other. And for the OR statement, there's no requirement of any overlap. So let's go ahead and do some examples. On the number line below, shade in all the values of x that solve the compound inequality. Now here, I didn't actually give you a number line. We can just sketch. So we have -3 is less than or equal to x. So what we can do is we can graph -3 is less than or equal to x. The way we'll do that is we'll draw a quick number line. We'll put a -3 over here. And then we want a filled in circle at -3. And then x bigger than, -3 less than x means our values of x are going to be bigger. So we would shade to the right. Next up, we have x is less than or equal to 5. So we'll draw a number line. We'll consider 5. Oops, that is equal to. We'll do a filled in circle at 5. And because x is less than 5, we will shade everything to the right. So now that we have our individual graphs, we can consider the intersection, -3 less than or equal to x less than or equal to 5. Right? Remember, this is where the graphs overlap each other if you were to put them on top of each other. So where does that happen? Well, what I like to do is I like to draw kind of dashed where those circles are. So we have -3, we have 5. We're going to do a closed circle here, closed circle here, and then everything in between those 2 points will be filled in, right? Because if you put the graphs on top of each other, that's where the overlap would be. Okay, next we have -2 less than or equal to x less than 3. So first we'll graph -2 less than or equal to x. So we'll do at -2, we'll draw a closed circle. And since x is bigger than -2, we'll shade to the right. We'll also graph x is less than 3. We'll do an open circle at 3. And then we'll shade to the left. And now we can do the compound inequality. -2 less than or equal to x, strictly less than 3. Now remember, this one we have to be really careful of, because at -2, because the graph is filled in both individual parts, it will be filled in for the compound inequality. But at 3, it's not filled in for 3, for the second graph. So that's actually going to be a open circle, because remember, it's where the shaded parts overlap each other. And the shaded part, there is no shaded part in the second graph, so there is no overlap once you actually put them on top of each other. And then lastly, we have our OR statement. So x is less than or equal to -2. And these ones do tend to be easier. We'll draw a circle at -2. It will be a filled in circle. And then we want points to the left. We have 3 is less than x. So draw a number line. In this case, at 3, we want an open circle. And then x is bigger than 3, so we'll shade to the right. So the intersection, x is less than or equal to -2, or 3 is greater than x. So did I say intersection? I meant to say union. So if you put the graphs on top of each other, that's the union. So the first graph on top of the second graph. Okay, so to summarize the graphs, once you understand that AND is the intersections and OR is simply on top of each other, what you do is you graph the individual components, and then the intersection is the overlap part for AND, and then there is no such requirement for the OR.